All right, hello everyone, and welcome to the very last lesson of Unit 4, which is on balancing redox reactions. So your objective today is to represent a balanced redox reaction equation using half reactions, and your essential knowledge is that balanced chemical equations for redox reactions can be constructed from half reactions. Redox reactions are reactions where electrons are transferred between substances, and to keep track of this, we separate the process into two parts called half reactions. And each half reaction will show the two components of a redox reaction, which are the oxidation and the reduction. So one of the half reactions is going to show a loss of electrons, and the other half reaction is going to show a gain of electrons. You can remember this using oil rig. So oil rig helps us remember that oxidation is loss and reduction is gain. Each half reaction is going to show one species losing electrons and the other gaining them. And when we balance redox reactions, we have to make sure that the number of electrons lost in oxidation equals the number of electrons gained in reduction. And once both half reactions are balanced, we combine them to create the final balanced redox equation where the electrons cancel out. In the oxidation half reaction, that's going to show the species losing electrons, which means our electrons are going to show up as products because we are losing them. And then in the reduction half reaction, it's going to show the species gaining electrons, which means our electrons are going to show up as reactants. So if we look at the chemical equation down here on the bottom, let's go ahead and do what we need to do first for any redox reaction, which is to assign our oxidation numbers. So for zinc by itself, in its elemental form, it's going to have an oxidation number of 0. Cu2 plus is going to have a +2 oxidation number because it's a monatomic ion. It's going to be the same as its charge. Same with Zn2 plus. And then copper is going to be elemental, so it's going to be 0. So we can see that zinc is going to lose 2 electrons because it's becoming more positive. So if it's losing 2 electrons, that means we're going to have Zn as our reactant. Then that's going to make Zn2 plus, and then it's going to lose 2 electrons. Now, same concept with our copper, except it is gaining 2 electrons. So those 2 electrons are going to be on the reactant side. So we have copper 2 plus our 2 electrons, and that is going to equal our copper or produce our copper. So you can see the charges are going to balance each other out in this reaction. So in the product side of the oxidation, you can see that we have 2 positives and 2 negatives. So those balance out to 0. And same concept for our reduction. We have 2 positives and 2 negatives, so those balance out to 0. And now that we've balanced our elements as well as our charge, we can look at our electrons. We have 2 electrons on each side, which will cancel each other out. So when we rewrite our redox reaction, it's going to be Zn plus Cu2 plus react to form Zn2 plus Cu, which is exactly what we started with, so it was already balanced. Now, it is not always that simple, and what we are mainly going to be focusing on in this lesson is the more complex redox reactions. So for those more complex redox reactions, we have a series of steps that you have to follow in order to balance them. And the big key here on identifying what needs to be balanced this way is if you have a redox reaction with oxygen and hydrogen that you cannot balance out normally. So the way that we do this is by first balancing atoms that are not hydrogen and oxygen. Once you have those balanced, you're going to balance your oxygen atoms by adding water to the other side. And then once you've added your water, you need to balance those hydrogens by adding H plus ions to the side that will cancel them out. Then you're going to make sure both half reactions cancel out with the same number of electrons. And then you are going to cancel out like species on each side and combine them to show your final balanced redox reaction. Now, some redox reactions take place in acidic solution where H plus ions are present, so we use that H plus when balancing hydrogen. Other redox reactions occur in basic solution where your OH minus ions are present. So we balance the H plus at the end with OH minus to represent that basic solution. So essentially, if you are in acidic solution, you're going to follow the steps that we're going to do on the next slide. If it's basic, you just have a few extra steps, and it's essentially getting rid of those H plus. If you are taking notes on this video, I would love for you to pause it here and record these 7 steps for balancing redox reactions under acidic conditions. Our first step is going to split that redox reaction into our 2 half reactions, the oxidation and the reduction. Then you're going to balance your non-oxygen and non-hydrogen atoms in each of those half reactions. Then you're going to balance the oxygens with water molecules. Then balance the hydrogens with hydrogen ions. Then you're going to look at the charge of your half reaction and balance that charge out to neutral with electrons. Then you're going to look at your 2 half reactions and make sure that the electrons are the same. If they are not, you need to multiply one or both of them to get them to the same number of electrons. And then you're going to combine the half equations, canceling out any like species on both sides. All right, so let's start off by assigning our oxidation numbers to figure out what is being oxidized and what is being reduced. So for our first species, we have ClO3 minus, which means we know this is equal to a -1 oxidation number. Each oxygen is -2, so times 3, that would give us an overall -6. And if we are solving for Cl, this means that our oxidation number for Cl is going to be +5, and for oxygen, it is -2. Now we're going to do the same thing for SO2. We know each oxygen is -2, so that's a total of -4, which means sulfur has to be +4, and each oxygen is -2 again. Then for SO4 minus or sulfate, we know it's equal to a -2 charge. Each oxygen is -2, so it's going to give us a total of -8, and we're solving for sulfur. So it's going to give us an oxidation number for sulfur of 6, oxygen -2, and then for chlorine, it's the same as its charge, which is -1. So now let's look at the species that are changing in oxidation number. So first we have chlorine. Chlorine is going from a +5 to a -1, which means it is gaining electrons because it's becoming more negative. So because it is gaining electrons, this is going to be reduced. So our reduced half reaction is going to include ClO3 minus and Cl minus. And then for our other half reaction will be the oxidation reaction. We have sulfur going from a +4 to a +6, which means it lost 2 electrons. So this is going to be oxidized. And this will be our other half reaction with SO2 and SO4 minus. So first step when balancing half reactions is you need to balance everything that is not oxygen and hydrogen. And we can see on our oxidation reaction, we have 1 sulfur on the left side and we have 1 sulfur on the right side. So those are already balanced. And same goes with our reduction half reaction. We have 1 chlorine and 1 chlorine. So we can move on to balancing our oxygens. So in our oxidization half reaction, we have 2 oxygens on the left and 4 oxygens on the right. So I need 2 additional oxygens on the left, and I'm going to do that by adding 2 water molecules. And now because I added water molecules, my hydrogens have nothing on the right side to cancel them out. So I'm going to add 4 H plus ions to cancel out those hydrogens that I used in water. Now let's do that exact same thing to our reduction half reaction. So we have 3 oxygens on the left, which means I need 3 water molecules. And now that I added 6 hydrogen atoms, I need to add 6 H plus ions to balance out the hydrogen. Now we need to balance out charge. And what I mean by that is your charge on your product side should equal the charge on your reactant side. So let's first start out with our oxidization half reaction. On the reactant side, we have no charge, so it's a charge of 0. On the product side right now, we have a charge of -2 from sulfate, and we also have a charge of +4 from our 4 hydrogen ions. Now, this gives us an overall charge of positive 2. And since we need this side to equal 0, we need 2 electrons to cancel that out. So I'm going to add 2 electrons to my product side. And now let's do the same thing for our reduction side. So we have on the product side an overall charge from the chlorine of -1. So that means on the reactant side, we also need to get that to a charge of -1. Right now we have a total of 6 positive and we have 1 negative. So in order to get that to 1 negative, we need to balance out this 6 with 6 electrons, and that will give us an overall -1 charge. So we're going to add 6 electrons to our reactant side. Now that our charges are balanced on both half reactions, we now need to make sure our electrons are the same in both half reactions, so when we combine them, they cancel each other out. And we can see in the reduction half equation, we have 6 electrons, and in the oxidation, we only have 2. So we need to multiply this entire equation by 3 in order to get that to 6 electrons. So we're now going to have 6 water molecules, 3 SO2, 3 SO4 2 minus, 12 H plus, and 6 electrons. So now that we have that, we are going to combine our oxidation half reaction and our reduction half reaction into one big happy reaction. So first, let's start off with our reactants. So reactants from the oxidation equation is 6 waters and 3 SO2 molecules. And then from our reduction equation, we have our 6 electrons, our 6 hydrogens, and our ClO3 minus. Now for our products, starting with the oxidation half reaction, we have 3 SO4 2 minus, we have 12 H plus, we have 6 electrons, and then from our reduction equation, we have Cl minus and 3 waters. So now we need to figure out, okay, what do we have multiple of that we need to cancel out? So first, most obviously, is our electrons. Those are gone. Then we also have H plus ions on both sides. So I have 6 on the left and 12 on the right. So that's going to turn to 6. And our water molecules. So I have 3 on the right and 6 on the left. So that's going to be changed to 3. And now that I have all of those canceled out, I can combine and get my final balanced redox reaction. So I have 3 water molecules. I have 3 SO2 molecules. I have a ClO3 minus. I have 3 SO4 2 minus. I have 6 H plus ions. I have a Cl minus. And that is our final balanced redox reaction. All right, yay, let's do it again. All right, so again, first part is going to be finding out those oxidation numbers. So manganese in MnO4 minus, we know it's going to equal -1. Each one of those oxygens is -2. So our manganese is going to be equal to +7, and each oxygen is -2. Remember, H2O2 is one of those exceptions, so each oxygen is -1. And then our hydrogen is each +1. And then this Mn2 plus is going to be a +2 oxidation number. And because oxygen is by itself, it has an oxidation number of 0. So manganese here is going from a +7 to a +2, which means we know it is gaining electrons. So that's going to be our reduction reaction. So it's going to be MnO4 minus and Mn2 plus. And then for our oxidation reaction, we will have our other 2 species. So that will be H2O2 and O2. So now let's go ahead and balance our non-hydrogen and non-oxygen elements, which are already balanced. So now we're going to balance our oxygens with water and our hydrogens with H plus ions. So starting off with the oxidation reaction, my oxygens are already balanced, so I'm going to use H plus ions, and I need 2 of them to balance out those 2 hydrogens. And now for our reduction side, we need to balance out our oxygens first. So I have 4 oxygens on the left, which means I need 4 waters on the right. And that is 8 hydrogens, so I need 8 H plus on the left side. So now I need to balance out my charges. So for our oxidation reaction, we have a total of 0 charge on the left side, which means I need to get to 0 on the right side. And right now I have a +2 charge. So I need 2 electrons to balance that out. So those are going to go on my product side. And now let's do the same thing with my reduction half reaction. I have an overall +2 charge on the right. And right now I have +8 and -1. So if I need to get this to an overall of a +2 charge, right now total I'm at a +7. So I need 5 electrons to balance that out. Now that our charges are balanced in both half equations, we need to balance out our electrons. Since it's a 2 and a 5, we're going to have to multiply both of them to get to our common multiple of 10. So this reaction is going to be multiplied by 5, and then our reduction equation is going to be multiplied by 2. So first let's do our oxidation. So we now have 5H2O2 react to form 5O2 plus 10H plus 10 electrons. And now let's do our reduction side. So 5 times 2 is 10 electrons plus 8 times 2 is 16 H plus 2 MnO4 minus. And then we have 2 Mn2 plus 8 waters. So now let's go and combine. And I know on the last slide I combined them and then canceled them out. That is just to minimize error. If you are looking at this and you can cancel them out first before you combine, I think it saves time. But if you're not comfortable with that yet, then you can do it the other way. So let's go ahead and show you the shortcut. So we have electrons on each side, so let's cancel those out. We have H plus ions on both sides. So we have 16 as our reactant and 10 as our product. So all of our products are going to be gone. We're going to be left with 6 H plus left on the reactant side. And then we are done canceling out. Everything else remains. So let's go ahead and combine. So for reactants, I have my 5H2O2 from the oxidation half reaction. And then I have my 6 H plus ions from the reduction half equation. And my 2 MnO4 minus. And then for the product side, I have my 5 oxygen gas molecules from the oxidation half equation. Then I have my 2 Mn2 plus from the reduction, as well as my 8 water molecules. So this is our final balanced redox reaction. Isn't that so fun? All right, so now let's add some more steps. So now, if it says under basic conditions, you're going to do the exact same thing we just did, but now at the end, you're going to balance out the H plus ions with hydroxides. So let's say you have 2 H plus ions as a product. That means you're going to put 2 hydroxide ions on both sides of the reaction. So the OH minus and the H plus that are on the same side form water, and then you're left with OH minus on the other side. So it essentially turns it into a basic solution. Then you're going to treat it exactly the same. All right, so now let's practice balancing a redox reaction under basic conditions. So let's first assign our oxidation numbers. So each hydrogen, since it's paired with a nonmetal, will be a +1, which makes this nitrogen a -3. This ClO minus is equal to a -1 oxidation number, and since oxygen is -2, that means each Cl is a +1. And then our hydrogens are again +1 because they're paired with a nonmetal, so that makes each nitrogen equal -2. And then this chlorine is equal to -1 because of the charge. So now let's go ahead and identify our components. So our chlorine is going from a +1 to a -1, which means it's gaining electrons. So that's going to be our reduction equation. So ClO minus and Cl minus. And then our nitrogen is going to be losing electrons because it's going from a -3 oxidation number to a -2. So that is going to be oxidized. So we have NH3 and N2H4. So now let's make sure our non-hydrogen and oxygens are balanced. On the reduction side, we only have one chlorine on each side, so that's already balanced. We do need to put a 2 in front of NH3 to balance out our nitrogens. So now let's balance out our hydrogens and oxygens. For the oxidization half reaction, there are no oxygens, so I'm going right to the hydrogens. I have a total of 6 on the left and 4 on the right, so I need 2 H pluses to balance that out. And then going over to my reduction side, I have 1 oxygen on the left, so I need 1 water on the right, which means I need 2 H plus ions on the left. So now I need to make sure my charges are balanced. So in the oxidization half reaction, I have a total of 0 charge on the reactant side, and then I have a 2+ charge on the product side. So I need 2 electrons to balance that out so that I have 0 on both sides. And then for the reduction side, I have a -1 charge on the right. So that means I need to get a -1 charge on the left. Right now I have +2 and -1, which gives me a +1 charge. So in order to get to -1, I need 2 electrons. And now I am balanced. So now let's cancel out our electrons, which are already 2 on each side. We also have 2 hydrogen ions on both sides, so those cancel out. And then we are done and ready to combine. So for our reactants, I have 2 NH3 plus our reactant from the reduction side, which is ClO minus. And then for our products on the oxidized side, I have N2H4. And on the reduction side, I have Cl minus and H2O. Now, if I'm under basic conditions, I need to look at my final equation and see, okay, if there are H plus ions somewhere, I need to put the same number of hydroxides on both sides and combine the H plus and the OH minus on that single side into water molecules. However, there are none here. So since there are none here, you are done. You do not have to do any steps. That was kind of a little surprise question. So now let's do one where that does not happen and you do end up with H plus ions on one side. All right, start off by assigning your oxidation numbers. So for aluminum and hydrogen, aluminum is a metal, so that's going to assume your positive charge. Hydrogen is going to have your negative charge. So each hydrogen is -1. And so if you want to put this in an algebraic equation, we have a total of -4 for hydrogen, and it's equal to the overall charge, which is -1. So X is equal to +3. Then for H2CO, we know our hydrogens are going to be positive because they are bonded to nonmetals, so a total of +2, and oxygen is -2, which means this carbon is going to have an oxidation number of 0. Each one of the hydrogens is +1, and the oxygen is -2. Then this aluminum is +3 because that's the charge on it. And then now let's look at our CH3OH. So each hydrogen is a +1 oxidation number. So that's a total of +4. And then we have a -2. So this carbon has to be a -2 to balance those out. So our carbon is going from a 0 to a -2, which means it is gaining electrons, which means it's reduced. So our reduction half reaction is going to be with H2CO and CH3OH. And then our oxidized half reaction is going to be with RAlH4- and RAl3+. So now you need to balance your non-hydrogen and oxygens, and if you look, our aluminums are balanced and our carbons are balanced, so we're good there. Now balance the oxygens and hydrogens. So for our oxidization half reaction, there are no oxygens, we just need to balance out the hydrogens. So I need 4 H+ ions on the right. And then for our reduction half equation, I do need to look at my O's, and I have 1 on each side, so do not need a balance. But for my hydrogens, I have 2 on the left and 4 on the right. So I need 2 more H+ ions on the left. And now I need to balance out my charge. So I have an overall -1 charge on the reactant side, and I have an overall +7 charge on the product side. So in order to get that to -1, I need 8 electrons. So I'm going to add 8 electrons on the product side. And then for my reduction side, I have an overall charge of 0 on the product side, and I have a 2+ charge on the reactant side. So I need 2 electrons to balance that out to 0. So now because I have 8 electrons in my oxidization half reaction and 2 in my reduction, I need to multiply this by 4 to get both to 8. So now I'll have 8 electrons, I'll have 8 H+ ions, I'll have 4 H2CO, then I will have 4 CH3OH. And now I can clearly see that my electrons are going to cancel out. I'm going to have 4 H+ ions left on the reactant side, and then everything else is balanced. So let's go ahead and combine those two half reactions. So for the reactants, I have AlH4-, and then I also have my other reactants from the reduction half equation. I have my 4 H+ ions, and I have my 4 H2CO. And now for my products, I have Al3+ from the oxidization half equation, and then I have my 4 CH3OH molecules. So in acidic conditions, we would now be done. However, this specifically is calling for basic conditions. So this is where the new steps come in. We look at where our H+ ions are, and we add that same number of hydroxide ions to both sides. So we are going to add 4 hydroxide ions to the left and 4 hydroxide ions to the right. Now, as you can tell, our OH- ions and our H+ ions are going to combine to form 4 moles of water. And because we don't have any water molecules present in this reaction and none of them cancel out, we are done. And this is our answer for balancing the redox equation in basic solution. All right, I hope this video helped. I hope you have a great day, and let me know if you have any questions, and feel free to comment below in the video. Bye.